Hello, this is Tim Smith, the Academic Support Coordinator for St. John's River State College, St. Augustine campus. This video, Graphing Trigonometric Functions, is designed as a study aid and supplement to the math tutoring services offered at St. John's River State College. It is recommended to view the video Trigonometry and the Unit Circle before watching this video. In this video, we'll be graphing trigonometric functions, graphing trigonometric functions with transformations, graphing functions with trigonometric elements, and determining the function of a given graph. First, we'll graph the function f of x is equal to sine x. In previous lessons, we have used the unit circle to find solutions for sine at common values of x in the domain. This time, we'll graph sine on a Cartesian coordinate graph labeled with multiple values of pi to give us round number solutions. For example, sine 0 is 0, sine pi over 2 is 1, sine pi is 0, sine 3 pi over 2 is negative 1, and sine 2 pi is 0. This cycle makes the period of sine 2 pi. Filling in all values generates a sine wave that continues through the domain from negative infinity to positive infinity. We can first observe that this graph is symmetric with respect to the origin, making sine an odd function. We can also use this graph to determine the range of sine x to be the interval from negative 1 to positive 1. The graph intercepts x at 0 and multiples of pi, and intercepts y at x equals 0. Maximums of 1 occur at pi over 2, 5 pi over 2, periodic at 2 pi. Minimums of negative 1 occur at 3 pi over 2 and 7 pi over 2, periodic with 2 pi. Next, let's graph the function f of x is equal to cosine x. Referencing the unit circle again, we can graph cosine on a Cartesian grid starting with the values cosine 0 is 1, cosine pi over 2 is 0, cosine pi is negative 1, cosine 3 pi over 2 is 0, and cosine 2 pi is 1. Like the sine function, cosine has a period of 2 pi. Completing this cycle leads to a cosine wave covering the domain of negative infinity to positive infinity. This also leads us to the same range as sine, that of negative 1 to positive 1. Observing the cosine graph on the Cartesian grid, we can see that it is symmetric across the y-axis and as such is an even function. X-intercepts happen at odd multiples of pi over 2, and the single y-intercept occurs at 1. The maximum of 1 occurs at even multiples of pi, and the minimum of negative 1 occurs at odd multiples of pi. f of x equals tangent x. By definition, tangent x is equal to sine x over cosine x. As such, the domain of tangent x will exclude all x's where cosine x equals 0, or all odd multiples of pi over 2. These values will be vertical asymptotes. The range of tangent x is negative infinity to positive infinity. The x-intercepts occur at the same place where sine x equals 0, or multiples of pi. And again, like sine, the y-intercept is 0. By observing this graph, it is clear that the function is symmetric with respect to the origin, and as such is an odd function. Tangent x will have maximums and minimums that approach infinity and negative infinity respectively, as the x values approach the vertical asymptotes. f of x equals secant x. This function is defined as 1 over cosine x, and like cosine x is an even function. We start with the cosine graph. This function will be equal to 1 when cosine x is equal to 1, and equal to negative 1 when cosine x is negative 1. When cosine x is between 0 and 1, secant x will be greater than or equal to 1. When cosine x is between negative 1 and 0, secant x will be less than or equal to negative 1. This continues to vertical asymptotes for values where cosine x equals 0, or at odd multiples of pi over 2. We can now apply this to the entire graph. When we remove the cosine x portion, we are left with the graph for secant x. We can use this to determine the domain to be the set of real numbers except odd multiples of pi over 2. This graph also gives us a range from negative infinity to 1 and 1 to positive infinity. This function will have no x-intercepts and a y-intercept at 1. This function will have maximums and minimums that approach infinity and negative infinity respectively as we get closer to the points of the vertical asymptotes. F of x equals cosecant x. This function is defined as 1 over sine x, and like sine x is an odd function. We start with the sine graph. This function will be equal to 1 when sine x is equal to 1, and equal to -1 when sine x is -1. When sine x is between 0 and 1, cosecant x will be greater than or equal to 1. When sine x is between -1 and 0, cosecant x will be less than or equal to -1. This continues to vertical asymptotes for values where sine x equals 0, or at 0 and multiples of pi. We can now apply this to the entire graph. When we remove the sine x portion, we are left with the graph for cosecant x. We can use this to determine the domain to be the set of real numbers except 0 and multiples of pi. This graph also gives us a range from -infinity to 1 and from 1 to positive infinity. This also means the function will have no x or y intercepts. It will, however, have maximums and minimums that approach infinity and negative infinity respectively as we get closer to the points of the vertical asymptotes. F of x equals cotangent x. By definition, cotangent x is equal to 1 over tangent x, or cosine x over sine x. If we start with the graph of tangent x, we can arrive at the cotangent graph by simply taking each value's reciprocal. Like the tangent x function, cotangent x is symmetric with respect to the origin, and as such is an odd function. The domain of cotangent will exclude all x's where sine x equals 0, or 0 and multiples of pi. These values will be vertical asymptotes. The range of cotangent x is -infinity to positive infinity. Since 0 is an asymptote, there will be no y-intercept. The x-intercepts occur at the same place where cosine x equals 0, which are all odd multiples of pi over 2. Like tangent x, cotangent x will have maximums and minimums that approach positive and negative infinity as we get closer to the points of the vertical asymptotes. Next, we will consider graphs of functions that are transformations of the sine and cosine functions. As an example, let's start with the graph of cosine x. We then evaluate the function f of x is equal to cosine x plus 2. This is a transformation that shifts the graph up by 2 units of measure. Note that the domain of the function, the interval from -infinity to positive infinity, is not affected by the transformation, but the range is. The range of the original function is the interval from -1 to +1, and the range of cosine x plus 2 is the interval from 1 to 3. Next, we'll graph a transformation of amplitude. For this, we'll start with f of x is equal to sine x. This transformation is created by multiplying the function by a value in front of the original function. In this example, we will use 3. This increases the amplitude of the function by a factor of 3. Again, this transformation does not affect the domain, but increases the range from -1 to +1 to -3 to +3. Next, we will evaluate the period of the trigonometric functions. We again start with the graph of cosine x. This function has a period of 2 pi. If we change the function using the transformation cosine ax, the period can be calculated as 2 pi over a. For this example, we'll use cosine 2x. Note the graph compresses to a period of 2 pi over 2, or pi. Conversely, if we change the function to cosine x over 2, the graph expands to a period of 4 pi. Lastly, let's evaluate a phase shift transformation. Starting with the sine graph, we can add or subtract a value from x prior to applying the trigonometric function. For example, sine x plus pi over 3. To understand what happens to this graph, we can simply see that an x value of -pi over 3 will result in taking sine of 0, which is 0. This means adding to the x value shifts the sine graph to the left by the amount of the value added. Conversely, if we subtract a value from x, like sine x minus pi over 3, the sine graph shifts to the right by the value subtracted. We can now use this information to graph various trigonometric functions. For example, f of x is equal to -3 cosine pi over 4 times x minus 1. We will start with the cosine graph, then adjust for the period, amplitude, and finally the vertical shift. We can first determine the period of the function by taking the normal 2 pi and dividing it by pi over 4. This gives us a new period of 8. Note we change the scale here so the proper period can be observed. Next, the amplitude is multiplied by -3. This increases the range to -3 to +3 and flips the graph with respect to the x-axis. Finally, vertically shift the graph down 1 unit of measure. We can now use the same techniques to arrive at a function given a graph. We first observe that the graph intersects the origin, just as a sine graph does. So we will start with f of x equals sine x. We note that the graph has maximums at -1 and +3, giving it a period of 4. We then take 2 pi and divide by 4 to arrive at pi over 2. This will be multiplied by x. The range of this graph is from -2 to +2, meaning the amplitude is 2, which goes in front of the sine function. Then note that from 0, the graph decreases to its minimum, meaning the graph is a negative of the sine function. This gives us our final answer. F of x is equal to -2 sine pi over 2 times x. In this example, we start with a study of hurricanes. Hurricanes are categorized using the Saffir-Simpson hurricane scale, with major hurricanes fitting into categories 3, 4, and 5. The graph depicts the number of major hurricanes in each decade from 1921 to 2010. First, we use a scatter plot to plot the data using the decades on the horizontal and the number of hurricanes on the vertical. At first glance, this scatter plot implies a sine or cosine relationship with the data. If so, we can create a function in the form f of x is equal to a times sine omega x minus phi plus b, where a is the amplitude, omega is the divisor of the period t, phi is the phase shift, and b is the vertical shift. Amplitude is derived simply as the largest value minus the smallest value divided by 2. On our scatter plot, that is 33 minus 16 divided by 2, or 17 over 2. That value can be placed in our function for a. The vertical shift is determined by adding the largest value and the smallest value and dividing by 2. In this case, it is 33 plus 16 over 2, or 49 over 2, which can then replace b in our function. We can determine the period t by looking at two similar values. The value 33 occurs at decade 4 and then again at decade 9, so the period is 5. Period is equal to 2 pi over omega, so omega equals 2 pi over t, or in our scatter plot, 2 pi over 5. To determine the horizontal shift, use the period t equals 5 and divide the interval 0, 5 into 4 sub-intervals of lengths 5 divided by 4. Centered on the local maximum of 4, these 4 intervals will be 6 over 4, 11 over 4, 11 over 4, 4, 4, 21 over 4, and 21 over 4, 26 over 4. The sine curve is increasing on the interval 11 over 4, 4, and decreasing on the interval 4, 21 over 4, with a local maximum at 4. Therefore, we must shift the graph of the function 4 minus 5 over 4 equals 11 over 4 units to the right by replacing x with x minus 11 over 4. Next, we multiply out to obtain a sine function of the correct form. If you have further questions on this or any other math topic, or wish in-person tutoring, please consult the Academic Support Coordinator on your respective campus. Thank you, and good luck with your studies.